Hello all. Today I'm going to be looking at another AI project. Recall that last time we had a look at estimating a function, or given some data, finding a function that best fits that data. Today I'm going to have a look at a slightly more complicated problem, which I'm calling 4 squares. So let's begin. So let's consider a 2 by 2 square with the subsquares numbered 1 to 4 for ease of reference. Now the subsquares here can be colored or not colored as shown in this slide, and we find that there are 16 different ways we can do this, and we want to group these or classify these in the following way. So naming these groups, we have single for one square being colored, vertical for the vertical or horizontal coloring, diagonal for the two diagonal colorings, full for when all 4 blocks are colored, empty for when none of them have been filled in, and L shape for this bottom group where 3 have been filled in. So we then assign numbers to each of these, and on top of that we also have a category number, which is the num divided by 6, which we'll see come into play later. And okay, so we want to use a neural network to classify these blocks. So we want a function where we put in as input one of these blocks and out comes what is the category this block belongs to. So as our inputs we have 1, 2, 3, 4, which is a 1 or 0, 1 meaning the block assigned to that number is colored, and 0 meaning it's not been colored. And I chose to model it like this. So we have the first layer, layer A, going to 6 nodes. So from the 4 input nodes, we go to 6 nodes. Then B takes us to 4 nodes, and layer C takes us to another 6 nodes. Then we have a final output taking us to 1 node, which outputs a number between 0 and 1. So that was the category num between 0 and 1. That's why we divided by 6. Previous slide. Okay. So of course in any of these nodes we take a weighted sum of the inputs, and we have a bias and we apply an activation function, the sigmoid function. So that looks like this. So taking in the inputs, we have weights, we take a weighted sum, and for each node here, y, we have a bias associated to that, and then we take activation, which we've selected the sigmoid for this project. So looking at an entire layer of these, this becomes a matrix, and in matrix form we get this. So the sigmoid applied to weighted sum of the inputs plus the bias, and taking this this matrix of weights as just the matrix A for layer A. We have this. Now, looking at that, yeah, I've just changed B to A to represent the biases that go along with the layer A. So applying to our inputs the first layer, then the second, then the third, and then the last output layer, this is what we get. So this function represents pushing our input through the neural network to get our output. Alright, now let's look at this in terms of the code. So we firstly define our neural networks, so that's defining all the layers and the functions that represent them. So here we have the first layer with our matrix A and bias vector small a. We have also similarly the second layer, third layer, and the output layer. We then also have some labeling and conversion functions. So these functions convert the category to the number associated with the category and the number back to the category. So these are some useful functions. And then we get to the creation of the test dataset. So if we recall, we are looking at categorizing 16 blocks. And so our test dataset comprises simply of these 16 rows where we have the square and the category. So we've modeled the square using a list of 4 numbers with 0 representing that the block is not filled and 1 representing that the block is filled. So here at number 6, 0, 1, 1, 0 says that block 1 is not filled, block 2 is filled, block 3 is filled, and block 4 is not filled, and that is in the group vertical. And here we calculate the category number, which is the number associated to the category that's between 0 and 1. So then we look at our initial testing. We get some test results. Of course, they're not very good. We're estimating, remember, the category number. So here's the category number we're supposed to get, and here's the category number obtained by pushing the test data through our neural network. So remember, our current neural network is just our initial random neural network. So there is the results. And we also have a scoring function which gives us the error. So our initial error is 1.872. So we also now move on to creating functions that iterate this process and update all our weights. So for all the matrices, A, B, C, and D, and the bias vectors A, B, C, and D, small letters. So here, these update functions use the epsilon, similar to our previous project with the functions. So that's the step that we use to step in the positive and negative direction and then calculate the error and see which one is better. And so here we've used a 0.1 epsilon and we've updated all our variables through 15 times. And we see that in generation 0 we had an error of 1.87. So that's the initial test, and in generation 15 we've managed to reduce that to 0.9428. So as an initial check, we just look at the initial and final value of A to make sure that indeed our variables are changing. And yes, indeed they are. Now looking at the test results, we see that here's our square, here's what our category, what we expect the category number to be. These are the test results numbers, and we're using our conversion functions to get the category numbers. So the category number for what the results are supposed to be and the category number for the actual test results, and we're checking are these equal and giving a score of 1 if it equals 0 if it's not. And through our 15 generations, we're seeing that we've managed to get 1, 2, 3, 4, 5 right, and everything else is wrong. So looking at some plots, see that our error has dropped from above 1.8 down to, I think it was 0.98 or something like that. And looking at how this went in terms of a score out of 16, we see that our initial random choice actually started with a score of 4, and our final generation 15 ended at 5, and epsilon didn't change throughout the 15 iterations. So let's just do this a few more times. I've just split it into 15 generations so we can see the progress. So let's run another 15 generations and see how this goes. See here we have more ones on the score, so we've learned something. And the plots also show we have error dropping further to about 0.7, and our score has climbed from 5 to 10 in these 15 generations. So running another 15 generations, let's see how far we can go, getting better results. Results seem the same. Let's see what the plots say. Yes, the error dropping down, but the score in terms of number staying the same. Staying the same there with epsilon. Let's just run another 15 generations and see what happens. And we're staying the same, a little bit of a drop. So let's, instead of going bit by bit, let's run a whole 100 generations from the beginning, so from a random start, so we can see a more long-term view of what's going on. So this time, looking at our test results, we've got, seems 15 out of 16, we've just missed one there. And looking at our plots, errors starting from over 1.4 and dropping to under 0.4 there in 100 generations. And our score starting, it seemed, at 1 with our random choice and climbing all the way to 15. And epsilon changed twice throughout this iteration, halving to 0.05 and then 0.025.